Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today, we're going to look at growing dots, and we're going to focus on growing dots as an expression, as a summary of a pattern. This correlates with the linear version of the lessons in the curriculum. In Unit 2, Topic 2, students learn to build equations recursively and explicitly as descriptions of recurring patterns. Here are some of the key ideas. Equations can be viewed as succinct descriptions of a pattern. The values of arithmetic sequences can produce a linear function whose domain is a set of integers. The values produced by an arithmetic sequence is the set of discrete values. The domain and range of linear functions are continuous over the entire domain. Some helpful skills. Students have learned in past courses that proportional reasoning with integers and rational numbers, and they've gotten that learning in Math 6, Math 7, and or IM. Coefficients represent the number of addends of a number. This is learned in elementary school and reinforced in Math 6. Numbers can be decomposed to reveal patterns. This is a particularly important skill that has been exhaustively done with students in elementary school, and it's going to be the basis for which we're able to observe patterns. Now, in the curriculum, we have a sequence of dots, but this is a similar task from NCTM. This is often represented with toothpicks or matchsticks, but the idea is to look at the number of lines or the perimeter of the triangles and the shapes that they form. In this case, we're going to focus on the total number of lines in any stage of this diagram. In the first stage of the diagram, I only have 3. In the second stage, 5. In the third stage, 7. In the fourth stage, 9. And while the fifth stage isn't represented, we would want students to hypothesize what that number would be so that we can see whether or not they're identifying the pattern. If they're able to identify the pattern and say that the fifth stage should have 11, we're set and we're going to be able to get students to recognize the patterns we need. To be able to do that, we're going to have to extend our table. So the next column that I'm going to add is going to be that decomposed number. It's going to be the total number of lines, but decomposed as we might see it in an elementary school classroom. We'll start with that first value, 3. We'll also be doing the total number of lines as a pattern of the addends. When we take a look at the decomposition of the numbers, we see that we start with 3, and that 5 is represented as 3 plus the 2. It's the recurring pattern. 7 is 3 plus the 2 plus the 2, and so on down the table. So the question is there a pattern that we can observe? And there absolutely is, and we want students to see it. So we're going to go to the total number of lines as a pattern. We already have enough to recursively write the equation. We can say that the initial value was 3, and that each time we added 2 to the previous term. The question now stems, how many times did we add 2 at any particular stage? Let's look at that pattern. In the first stage, we have 3 plus no addends of 2. In the second stage, we have 3 plus 1 addend of 2. In the third stage, we have 3 plus 2 addends of 2, and so on. At this point, we want to draw students' attention to the stage and the number in the parentheses. We want them to be able to look across the table and see if there's a rule that they can write that connects these two. With 1, it was 0. With 2, it was 1. With 3, it was 2. With 4, it was 3. And with 5, it was 4. So the question is that for any number n, what do we need to do to determine the number that should go in those parentheses? Students may say it's 1 less or subtract 1. All of those are exactly what we want to hear students say. What we have to do is then use that to develop an expression. If we have n, we really need n minus 1. And so the expression for this is 3 plus 2 times the quantity, n minus 1. Explicitly, what we're really saying is that the number of 2's is 1 less than whatever stage we're on. F of x equals 3 plus 2 times the quantity, x minus 1. Notice that the 2, which is the slope, occurs as the repeated pattern and the slope inside the function. This is a key learning we want students to identify. We also want them to identify that the initial term, 3, is the constant. A lot of people may ask, why did you start the table at 1? Shouldn't we start it at stage 0? Well, actually, students are best served seeing both and making some observations. So let's take a look at that previous task. We started the table at 1, and we ended up with 3 plus 2 times the quantity, n minus 1. This time we're going to do a similar task and a similar process, but we'll start with 0. So we have a stage 0, and then we have some values, 0, 17, 1, 13, 2, 9, 3, 5, 4, 1. So it looks like each time we're subtracting 4. We're going to extend our table, and we're going to see what those patterns reveal. First, let's decompose the numbers. 17. 13 is 17 minus 4. 9 is 17 minus 4 and minus 4 again, and so on. Let's rewrite those as patterns. In stage 0, we have 0 deductions of 4. In stage 1, we subtracted 4 once. In stage 2, we subtracted 4 twice. At this point, we're going to ask students to make some observations and some conclusions, keying in on the stage and how it's connected to the number of addends. Students will likely pick up that the stage and the number of addends is the same. So our equation in this situation, or expression, is 17 minus 4n. So here's the question, what difference did it make? Why is it that we have an n minus 1 versus an n? Well, we're going to rewrite that n, but we're going to rewrite it as an equivalent expression. We're going to rewrite it as n minus 0. Because there's a really important observation that's the basis for point-slope form, something that students will encounter later. Notice that whatever is deducted from the variable is the same as our initial domain value. Also notice that the constant is the same as our initial range value. So ultimately, it doesn't matter where we start the table, as long as we recognize that whatever our starting term is, we're going to use the domain value inside the parentheses, and we're going to use the range value as the constant. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below. Thank you, and have a nice day.